Welcome back to the Grand Solar Minimum channel. Today is Wednesday, January 8th, not the 7th, folks. Good Lord, we need to get our stuff together over here, don't we? It's been a long time, a little rusty here, but I have been watching everything from afar. And I'll tell you what, I've had just about enough. I've seen everyone's comments on our YouTube channel, because we have been, let's just say, not been on the air for quite some time. In fact, June 30th was the last live update we had. And just life, guys, jobs kind of take over. And trust me, I want to be active on this channel. But life takes over. You have wife, you got kids, you got things going on with work. But I am sick of seeing all the naysayers out there and all the misinformation that's being spread about Grand Solar Minimum, and everybody's doing a touchdown dance because we were in the middle of a maximum of the solar cycle 25, which I'm going to show you guys exactly where we are and if indeed we are still heading into a Grand Solar Minimum. I will show you that. Everybody's doing a touchdown. All right, so let's get started with our space weather report. Our solar wind speeds are at 437.2 kilometers per second with a density of 2.48, sunspot number 113. And I want to talk about that real quick. So we've had a very active sun over this summer. No question about that. We saw sunspot numbers climb into the 300s for the smooth sunspot number. We've seen it hang out in the 200s for a while. About a week and a half ago, we had sunspot numbers at 63. Just earlier in the week, we were looking at geomagnetic storms and sunspot value numbers again in the 200s, but now we see it is now down to 113. And I'll show you guys, well, you can see right there in front of you that the eastern limb is not really going to produce a whole lot so far that we see. Now, there is a big, large area of plaque, or I should say plage, that is coming around the bend from the northeast or the eastern side of the limb. You guys can see that. But we really haven't had a lot of action when it comes to solar activity in solar cycle 25. You can make the argument that we had several X flares since January 3rd. In fact, sunspot AR 3947 has produced 3 small X flares, 1.1, 1.1, 1.2, and dozens of M-class solar flares. All that activity yielded 0 significant CMEs. What happened? Flares and CMEs are 2 different aspects of exploding sunspots, and they don't always happen at the same time. Dozens of flares with 0 CMEs is a little unusual, but not unprecedented. The opposite can happen too. AR 3947 might suddenly start producing CMEs with no significant flares. It would certainly prove for beautiful aurora forecasts as well. So all those X-class solar flares that I was monitoring closely myself amounted to nothing. We did have a severe G4, G3 storm that was short-lived. We got to a KP8, but that had nothing to do with those X-class flares. In fact, those were before the X-class flares. So just another example of the sun is not as strong as everybody thinks it is. And we all know about the SAA, the South Atlantic Anomaly, where scientists are becoming a little bit more worried about how weak the magnetic field is just around Southwest Africa and into parts of South America. On top of that, we're dealing with the weaker sun right now. And I'm not making this up. I'm not sensationalizing everything. I'll show you right now how we are still weakening when it comes to the sun. Let's go to our main screen. Let's see if this article will come up. Here we go. Let's get right into it, shall we? Check out our sunspot cycle. This is 25 where my arrow is. We're right at the peak. We're actually going to be coming out of this peak soon. And don't take my words for it. Valentina Zarkova wrote a paper back in 2019 that got all kinds of bad press. It was accepted in nature.com, and then they retracted it. So people were pretty much downplaying her forecast as it wasn't accurate, so it's not going to happen. The things that got that paper retracted were calculations that did not matter in the overall scheme of things. Excuse me. Got a little bit of cold here. But as you can see, we're still dealing in the maximum, but look at where our peak is compared to solar cycle 24. There were folks out there who had predicted that we could possibly see a stronger, slightly stronger solar cycle 25 or slightly weaker solar cycle 25. If we are at the peak and we start coming down rapidly like Zarkova has predicted, nobody will remember the active summer that we had. And when you compare it to solar cycle 24, it is slightly higher. Compare solar cycle 25 to 23, we're nowhere near that. We're nowhere near what we were in 22. We're nowhere near what we were in 21. Hell, look at solar cycle 19. Look at that is the peak of this modern grand solar minimum, or I should say modern warming trend. This was the peak. Okay? This is when we started seeing temperature rise. How ironic is that? The sun has the highest output in 100 years, and we start to see global temperatures start to go up. Unreal, isn't it? The sun causing all that. That's crazy. That's crazy. Say hello to a few people out there in the chat so far. Matthew McDonald, how's it going? Long time no see. Firewheel Farm, what's up? Jesse Vorwald, our friend up there in Wisconsin. And of course, Rebecca H. Lori, good to see you guys. Thanks for tuning in on this makeshift episode here. I just had to do it. I couldn't help it. But so when you look at where we were in the peak of this modern warming trend that we've had, and solar activity going up and up and up and up until right after the 60s, and we have slowly declined since then. Now, I know that we've seen the good old-fashioned map that shows what happened during the Maunder minimum. And I'm actually going to look for that chart right now because I wanted to discuss a little bit about that as well. I don't think we are currently being correct about how this solar cycles happen, how the idea of zero sunspots. And I hate to be this picky, but it has to be done. So if you look down here during the modern minimum, right, and you hear that zero sunspots for 50 years, well, you see these little X's. Galileo and company saw sunspots. Okay, so there wasn't zero sunspots. All right, this graph is just smoothed out. But where I'm going with this, and even in 1750, 1800, 1850, sure, we had telescopes. Sure, we had more modern equipment as we got to the 1900s. And of course, satellite data came out right around here. But if you look at these peaks, look at the Maunder minimum, peak, Dalton minimum, peak, and then not really seeing. Now, we did have the slight minimum here in 1911, 1912. There was some serious flooding here before 1900 and during the early 1900s. We had some low solar activity, just as low as almost as what we're seeing right now. And then we get to a maximum modern maximum in the late 60s, or I'm sorry, the late 50s, early 60s. And now we're trending down towards a minimum grand solar minimum. Some of us will call it the Eddy minimum. That's the way I was taught anyway. this upcoming solar cycle will be referred to as the eddy minimum. But I just wanted to show this graph for context so that people can stop freaking out as if this summer of activity had made us so active that the GSM was canceled. And to those people who are saying that, you never did pay attention, did you? Not once. Because nobody in the grand solar minimum community ever said that this was an overnight thing. We said this from day one. It's going to take time to see the results. It's going to take time to see the differences. It's not just going to happen overnight. Now, 2024 is being argued as the warmest year in modern times during the satellite era. How can we deny that, right? We saw the global temperatures peak over 1.02 degrees Celsius above baseline. There's no denying that. But there's also no denying back in January of 2022, we had a huge explosion from an underground volcano known as Tonga that shot an ash plume 122,000 feet up into the air that carried water vapor. And since then, we have seen large amounts of moisture in the part of the atmosphere that usually doesn't see that, if ever. When asked a scientist, a person who I've trusted throughout the years, but I think his payroll is more worrisome than telling the truth now. I asked if the water vapor from Tonga had any effect whatsoever on the warming temperatures that we had for the past 6 months. Now starting to cool. We're at 0.062, by the way. I'm sorry, 0.62 above baseline. And that scientist told me no. That the water vapor from Tonga in the atmosphere in 2022 had nothing to do with this summer's anomaly. And it's an anomaly, folks. Our temperatures were trending on the cooler side until that volcanic eruption. And when you put sunlight and water vapor, it's going to produce more heat. It's going to produce more warmth. And that's what happened. Parts of the atmosphere were warming that we don't usually see warming. And that Tonga volcano eruption really messed with a lot of predictions when it came to global temperatures. Some folks are still in denial about this. And that's fine, because time will tell. And I've been watching this cycle, even though we haven't broadcasted regularly. I still watch this every single day. I check the numbers every single day. Climate as well. And what's happening? I want to see if this works out right for me, guys. This is a test. Sorry to do this here. I'm kind of pulling a Lee Wheelbarger here. He likes to run audio tests during his broadcast. Hold on a second. I've learned for the best.
Hello, I'm Dr. Ronan Conley. We've just published an important new peer-reviewed paper in APJ, the Astrophysical Journal. In this paper, we're looking at changes in the energy coming from the sun, the total solar radiance, or TSI for short, during the satellite era. That's from 1978 to present. This is something that most people who've thought about it have assumed that it should be a fairly straightforward problem.
Okay, so this is a very, very, very good informational video. And I want you guys to pay attention here. This is Dr. Rowan Connolly. He also works with Dr. Willie Soon. And they did a paper on TSI. And I wanted to make this part of our broadcast because this confirms a few things about solar activity, solar output, and the lack thereof. So let's go ahead and continue here. I'll stop it in between to kind of help explain things, but I think Rowan does a really good job, and this is a very important video. So here we go. We got some information on some TSI finally, right?
but it is surprisingly challenging and controversial. In our new paper, we've discovered and shown that there were major problems with the main satellite composites that many scientists have been relying on. In this video, I'll dig into the details and summarize our key findings. It is quite a complex subject and it may get a bit technical in places, but I'll try to explain things as I go. So if you're interested in learning more about what we know about the fascinating star that we call the Sun, then let's begin. In the early 1600s, with the invention of the telescope, Galileo Galilei and others began pointing the telescope at the sun. Of course, you shouldn't look directly at the sun through a telescope without a special filter. But if you shine the eyepiece of a telescope onto paper, it's possible to see features on the sun's surface. So Galileo and others, when they started doing that, they noticed dark spots would often appear on the surface of the sun and last several weeks before disappearing. Every day as the sun rotated around its axis, these sunspots would rotate with it. This was a shocking discovery. Previously, it had been assumed that the sun was a perfect sphere that never changed. So, while most of the early astronomers used their telescopes for studying the night sky, as astronomers do today, a few would also use their telescope in the daytime to draw sketches of the sunspots. One of those observers was the German astronomer Heinrich Schwab. In the 1840s, he kept a continuous record of sunspots lasting 17 years. He discovered at the end that the number of sunspots seemed to follow a distinct cycle, lasting, he estimated, about 10 years. He found after months with no sunspots, the sunspots would start to increase every year for several years in a row, reach a maximum, and then for the next few years, the sunspot numbers would decrease all the way back to zero. A Swiss astronomer called Rudolf Wolf was so excited by Schwab.
Again, I don't believe that we ever hit zero sunspots for an entire year. I believe we might have seen a time with zero sunspots maybe for a day, but I don't believe that we were totally blank. In fact, to just kind of reiterate, you heard how Rowan was describing how they monitored sunspots, and it wasn't the most precise technology. It was the best they could do with it. So I still think sunspot numbers were underreported back in the times of Galileo and those other folks that he's speaking of here in the early days.
Schwab's discovery of a sunspot cycle, he decided to collect all of the sunspot observations he could find to see if it was true. He discovered that, yes, there is a cycle. It wasn't a strict cycle in that the length can change from 8 years up to 14 years, but it was Schwab was right, and the average is about 11 years. Now, we now usually describe solar activity in terms of these sunspot cycles. They're so well defined. We call them the solar cycles, starting with solar cycle 1 in the 1750s. Currently, we're approaching the maximum of solar cycle 25. So, the sun shows changes in sunspot activity, but does the actual energy output from the sun also change over time? And if so, could it contribute to climate change? Samuel Langley was an aviation pioneer. He was one of the inventors developing the first airplanes at the end of the 19th century, early 20th century. So he'd invented some of the first unpiloted planes in the late 19th century, and he was also involved in the race for developing the first manned planes. And that race was eventually won by engineers like the Brazilian Santos Dumont, the North American Wright brothers. But Langley's contributions were so significant that the US's first aeronautic laboratory was named after him. And that later became what's now NASA's Langley Research Center in Virginia. Langley was also an astronomer, and he was very interested in the possibility that the sun's energy might change over time. And he wondered whether, if that was happening, it might contribute to climate change. In an important paper published in APJ in 1904, he called on scientists to begin systematically trying to monitor the solar radiation reaching the Earth. Now, he warned, however, that any attempt to do so would be imperfect. He realized that measuring the sun's energy from ground was not a direct measurement of the energy that reached the Earth's atmosphere. Instead, it was just whatever hadn't been absorbed or reflected away by the atmosphere on the way down. Still, at the time, the idea of flying up high enough to leave the Earth's atmosphere was still complete science fiction. So Langley decided it was the best they could do for the time being. In 1890, he had founded the Smithsonian Astrophysical Observatory, SAO. So he organized a measurement program at the SAO that would continue until 1962. Years after the SAO program had ended, a scientist called Doug Hoyt tried to see if he could find any trends in the data. Unfortunately, he discovered Langley's concerns had been correct. It turns out that the variations in the SAO measurements seem to have been dominated by changes in local weather, observing conditions, differences between the instruments used for each set of observations. So it seems Langley was right. If we want to properly monitor the changes in the sun's energy, we need to do so from above the Earth's atmosphere. Now, fortunately, by 1979, that was no longer science fiction. We are now capable of launching satellites. In fact, Doug was on the science team in charge of the first satellite mission to continuously monitor the sun from space, Nimbus 7. In 1980, the second satellite mission was also launched for TSI. The first ACRIM instrument was launched on NASA's SMM satellite. By this stage, we had more than 350 years of sunspot observations. So one of the first questions that scientists wanted to answer was, is there a relationship between sunspots and TSI? And if so, what is it? People have been speculating on different possibilities. In 1976, Jack Eddy had pointed out in the journal Science that in the mid-1600s, there was a period when sunspots had almost completely disappeared for about 70 years. Climate scientists had noticed that was also a period of global cooling, what we now call the Little Ice Age. He suggested that maybe that wasn't a coincidence.
All right, keep paying attention because now it kind of gets into the nitty gritty of the TSI part of this paper and how it affects cooling and also warming.
But without direct TSI measurements, we couldn't know. So roughly, there were three competing hypotheses on the relationship between sunspot activity and TSI. One, the sunspots are dark features, so maybe when sunspots are there, that reduces the amount of TSI leaving the sun. Two, on the other hand, you could have when sunspot numbers increase, sun seems to become more active, more solar flares, more solar eruptions. So maybe less sunspot activity means less TSI and global cooling. Or maybe TSI behaves independently of the changes in sunspot activity. As we'll discover, it turns out that all three of those hypotheses were partly right and partly wrong.
By the way, I want to add Rowan is a guitar player, so that I'm almost 100% positive that's Rowan's little jingle there to switch the graphics and everything. So just wanted to add that little tidbit. All right.
This graph where I see here the first year of the ACRIM 1 satellite measurements on the top here. And at the bottom, we have the daily sunspot numbers at the same time. You notice that when a large sunspot group passes by and you get a high sunspot numbers, that's often associated with a sudden drop in TSI of a couple of watts per meter squared. You can see I've shown 3 examples here. So if we could look at this is a graph here, you can see that this is TSI and this is the number of sunspots. And you can see that on average, the higher the sunspot numbers, the lower the TSI. There's a relationship there over the course of 1 year. But if we look at 10 years of data, this is the entire ACRIM 1 satellite mission. It lasted nearly 10 years.
Notice the peaks at the bottom of sunspots are almost followed a huge drop in TSI. And here's what I mean by that. Let me get my little handy dandy arrow here. So if you see right here where the peaks are, look where the TSI drops really low when we're during these peak times. And he talks about this as well during the video. I'll shut up now.
Notice how we're seeing that as the sunspot numbers reach the solar minimum, TSI also decreases to a minimum, and then it increases again. So when we look, instead of looking at just 1 year, if we look at 10 years, we find that the relationship between TSI and sunspot numbers is actually reversed. You now get an increase in TSI with increasing sunspot numbers. So we seem to have stumbled onto a scientific paradox. 1 year's data proves hypothesis 1, 10 years data proves the opposite hypothesis. What was going on? As often happens in science, things are more complicated than we expect. Turns out that when sunspot activity increases, it's not just sunspots that are increasing. Bright features on the sun called faculae and plages also become more common. They're harder to see on the sun than sunspots. It is easier to spot a dark patch on a bright object like the sun than to spot a bright object on a bright object. You know what I mean? So we don't have as much data on faculae as we do on the sunspots. But these 2 NASA videos are based on data from NASA's SDO spacecraft. They show 1 month's observation of the sun near a solar maximum in April 2014. We can see the sunspots clearly in the video on the left, which is based on HMI magnetic readings. On the video on the right uses a 1700 angstrom filter, which makes it easier to see the faculae. Notice how, with the filter, around each dark sunspot, there are large bright regions, faculae. Also, notice there's networks of bright features across the sun's surface that aren't as obvious from the video or associated with sunspots. This explains why over the course of a solar cycle, sunspot activity is correlated to TSI. That is, when sunspot activity increases, faculae activity also increases. These bright faculae increase TSI more than the dark spots decrease it. But does that coincidental relationship between sunspot activity, faculae, and TSI remain the same over multiple solar cycles? That's been a controversial debate that's been ongoing since the late 1990s. here are the four main TSI missions launched between 1978 and the early 1990s. Do you notice how none of these records?
I wanted to pause this real quick too because he mentioned something about high sunspot activity in facula. And facula is that really bright feature that's on the sun around these sunspots. Now we've talked about how the sunspots represent a cooling of the area on the sun. Those dark spots are actually surface temperatures on the sun are cooler. But when you factor in the facula that goes around the sunspot, there's less area of cooling and more area of warming. So the bright facula and the output from the sun contributes to warming. And thinking of this summer with all that water vapor that's in the atmosphere from Tonga and the kind of summer that we did have. We had an active summer. We had a lot of sunspots. We had a lot of facula. The sun's output was definitely a lot higher than what we've seen, especially since we've been on the air with this channel.
Spans more than 2 solar cycles. That means if you want to study the intercycle changes, you need to combine multiple records into a single composite record. The ACRIM team, led by Dr. Dick Wilson, was the first group to develop a TSI satellite composite record. They prioritized their own ACRIM satellites since these were high-quality instruments designed solely for measuring TSI. They also used Nimbus 7 data to fill in missing gaps. The ACRIM team updated their composite multiple times during the 90s and early 2000s. The third and final ACRIM satellite was launched in 2000 and it ran up to early 2013. In this graph, I'm plotting the final ACRIM composite from 1978 to 2013. Now we're looking at 3 solar minima. That's how long we're doing, and you can see nearly 4 solar maxima. Notice how every solar minimum is always the exact same value, 0. You can't have less than 0 sunspots. But the TSI in each minimum is different. Also, we can see that the TSI during the solar maxima shows different behavior, slightly different behavior than you see for the sunspot numbers. That is, on short time scales, sunspots decrease TSI. Over the course of the solar cycle, TSI rises and falls in tandem with sunspot numbers. But over longer time scales, TSI can also change between solar cycles. This had 2 immediate consequences. First, it meant that relying on sunspot numbers was not good enough for working out how TSI had changed over the centuries. So, according to the ACRIM composite, it's true that there is a linear relationship between sunspot numbers and TSI, but the key point here is that the changes in monthly sunspot numbers can only explain 47% of the monthly TSI changes. So some other aspects of TSI variability are not being captured by the sunspot record. A second consequence was that the ACRIM composite showed an increase in TSI between the solar minimum in the mid-1980s and the next solar minimum in the mid-1990s. The 1980s and 1990s were a period of global warming, and the UN and others had been claiming that global warming was due to increasing greenhouse gases. But the ACRIM composite suggested that at least some of that global warming might actually be due to increasing TSI. Then, later, in the early 21st century, global temperatures famously entered a temperature hiatus, where temperatures neither rose nor fell for more than 15 years. And that was a period when, coincidentally, the ACRIM composite suggested a slight decrease in TSI, Was this just a coincidence, or did it suggest that maybe climate scientists had been underestimating the sun's role in recent climate change? Starting in the late 1990s, two scientists, Professor Klaus Froelich and Dr. Judith Lean, decided they didn't like the ACRIM results. They decided they would develop their own rival TSI composite. Professor Froelich was the director of the PMOD observatory in Davos, Switzerland, so their composite came to be known as the PMOD composite. In an interview for a NASA website in 2003, Dr. Lean explained one of the motivations for them to develop the PMOD composite was because they were worried that the ACRIM results might make people think that global warming could have a natural explanation and that might interfere with international greenhouse gas policies. So they decided that each of the satellite records used by ACRIM needed to be adjusted. Their adjustments were different for each satellite. But what was the net effect of PMOD's various adjustments and data choices? Here is the PMOD satellite record. If you remember, for the ACRIM composite, we were finding a lot of variation in TSI between each solar minimum, but now that's all gone. It's almost exactly the same for each minimum, exact same as sunspot numbers. Also, we can see that a lot of the variability in the sunspot, in TSI, in the sunspot maxima has also been removed. We now have almost exactly the same for both maxima and minima. As a result, you can see here that we have an almost exact linear relationship between the sunspot numbers and TSI over the entire satellite record. And you can see that the sunspot numbers can explain roughly 58% of the monthly TSI changes. That figure is even greater for the yearly values, which we discuss in the paper. The PMOD composite rapidly became popular with researchers who think TSI can't explain any recent warming. And because of that popularity, many other scientists who were unfamiliar with the details started assuming PMOD was the best one, simply because everyone else seemed to be using it. But today, a lot of the scientific literature you'll see assumes PMOD is correct. But is PMOD a more reliable composite than ACRIM? In 2008, Professor Nicola Scaffetta of the ACRIM team reached out to Doug Hoyt, the lead scientist at Nimbus 7, to ask him what they thought of Froelich and Lean's adjustments to their data. You might remember Doug was also that scientist I mentioned earlier who analyzed Langley's solar constant data in that 1979 paper. He completely disagreed with the PMOD's adjustments to Nimbus 7. As well as finding the adjustments to be unjustified, he argued that they were physically implausible. The ACRIM team also disagreed with the PMOD adjustments. As we discussed in the paper, the debates between ACRIM and PMOD over how TSI changed between those two solar minima in the 1980s and 90s have continued for decades, and they're still ongoing. But in our new paper, we show there's also controversy over the TSI trends since then. With the ACRIM PMOD debate, the main problem is a shortage of satellite data in the 1980s and early 90s. But since 1996, there have been multiple satellite missions available, and many of these have lasted more than one solar cycle. So now the challenge is deciding which satellite missions are the most reliable. These are the 5 TSI records launched since 1996 that have more than a few years of data. And you can see 3 of them are still active, and ACRIM 3 and Source each had more than one solar cycle's worth of data, 13 years, 17 years. And that at any one point there was at least 2 and up to 3 or 4 satellite missions available at the same time. And that initially sounds like a great thing, except.
Interesting, guys. Look at the chart here that talks about the missions that were still in progress. And there is a TSI S-1 that was started up in December 1st of 2018. It is still active. There are several other missions that are still active. SOHO, and I guess this is where we start to dig for information on current TSI readings. Now, if you guys remember, folks like Wood Spirit, who's been around for a long, long time, we used to report the TSI on a daily basis. We wanted to show you that the sun was actually losing strength. And it wasn't just some kind of sensational thing to say to get viewers and clicks. And I think for the first couple of years this channel was up and going, our broadcast would report TSI. Excuse me. And we started to point out the trend that was happening right before our eyes. And we were seeing, during the minimum, lower TSI. I'd love to see the TSI numbers today. I'd love to see what kind of numbers we're looking at during a maximum. This channel was birthed right at the beginning of the minimum of solar cycle 24. We were coming out of a maximum. It was 2016. We were wrapping it up. Things were starting to get low on the solar activity side. So we were monitoring TSI around 1361 point whatever. And we saw it get as low as 1359 point. I can't remember the point part, but we saw it dip into the 1359 range. And that's per squared meter, watts per squared meter. It was 1359 watts per squared meter. It's been a long time since we've had to say that. So I had to remember how that was actually pronounced. And Lee Wheelbarger, I'll give him credit for this because this is the guy that kind of introduced me into the solar science of climate change. And he introduced me to everything we're talking about right now. The TSI, sunspots, everything. But with that said, no, I don't think Ice Age 2025. I do think a very cold winter. But we're still too early in the grand solar minimum to see those really, really bitterly cold temperatures. I know some of you are disagreeing with me right now because we are seeing one of the coldest winters shaping up right now in the last 5 years. That doesn't mean we go to our platforms and ring the alarm, Ice Age. No, but this is the beginning, folks. We've been saying that since 2016. And it takes time, slowly but surely. Not overnight. It's not over a year, and it's definitely decadal. You'll see the bigger impacts are coming. Let's just put it that way. Solar cycle 25's minimum cycle is going to be interesting to monitor. And right now, like I said earlier in the broadcast, this cycle is not that strong. Folks, an X 1.1 solar flare is a really strong M flare. That's it. It's a really, really strong M flare. X 1.2, big deal. Now, in the summertime, we did have some stronger flares in the teens, but we haven't seen anything like the Halloween storm that we had many years ago. I think that was an X35, X40. That actually damaged power grids. I know I can speak off the top of my head. I believe it was Toronto, somewhere in Canada, suffered some grid damage. Power went down. Severe geomagnetic storm off of an X-class 37 type flare, maybe higher. Okay. That doesn't mean that we were in the strongest of solar activities back then. I think that was around 2003. So you're talking solar cycle 21, 22, something like that. Coming out of a strong modern maximum. That's why we still saw X-class flares in the 37 to 40 range. The peak has already passed us. This maximum part of the cycle is kicking and screaming its way out the door. It does not want to leave us, folks. But I think the point of this paper, and please check this video out on Dr. Rowan Connolly's site, is that there is significant correlation between TSI and temperatures here on Earth. And I would love if we could get our users active here. I'm currently looking for a live, up-to-date, real-time monitoring of TSI. I'd like to know what the reading of TSI is today. And I know we have a lot of subscribers out there who really get into this research, and I'm confident we'll find some kind of source that we can start reporting this again, because ever since the TIM, the source that closed in 2020, February 26th of 2020 to be accurate, we have not reported a TSI reading since that date. And it is almost impossible to find TSI data that is up to date, real time. So check that out. All right, let's move it along here. I didn't really want to spend that much time on that video, but Rowan has a lot of good work. He has a lot of good things to say. Saw this article here. Parker Solar Probe confirms safe status after record-breaking solar encounter. This has been in the news quite a bit. Closest approach ever to the sun. This is just an artist's image. This is not real, live, up-to-date footage of the satellite near the sun. If so, who's taking the picture, right? I don't see a selfie stick. The telemetry data was received by mission operators at the Johns Hopkins Applied Physics Laboratory, APL for short, in Laurel, Maryland on January 1st, 2025. It confirmed the Parker Solar Probe remains in excellent condition after its record solar flyby on Christmas Eve 2024. The data revealed that the spacecraft's instrument successfully operated during the perihelion, with further science data transmission scheduled for later this month. Mission operators at APL analyzed the telemetry, which indicated that the probe's heat shield and instruments had successfully withstood temperatures exceeding 2,500 degrees Fahrenheit and intense solar radiation. Spacecraft traveled along at 700,000 kilometers per hour, that's 435,000 miles per hour, and broke its previous records for speed and proximity to the sun. That is absolutely an awesome time to be alive, guys, to be able to see this. The Parker Probe. Hopefully we understand the magnetics of the sun more and more as we get further along with the research for the Parker Probe. Just another reminder of where we are in our solar cycles. Clearly you can see that solar activity is trending towards the bottom. We are approaching another grand solar minimum, a cycle that happens every 350 to 415 years. And we're alive to see it, guys. Outstanding. Outstanding. Taking a look in the chat, and I see we got 32 degrees in Jacksonville this morning. You guys must be freezing your begonias off. I had a guy complaining about 50 degrees in Florida, telling everybody that 50 feels like 25 degrees. Wah. But I feel your pain. 32 degrees in Jacksonville, guys. Again, cold winter so far. It's been like this probably, what, mid-December for most of the eastern and the southern parts of the United States. After having record temperatures, record heat over the summer. You know, I do remember this channel saying we are going to experience during the grand solar minimum short hot summers and long cold winters. And it started to get winter conditions out here December 1st, here in upstate New York. I see Jerome out there in Rochester. He's about 3.5 hours away from me. And they woke up today with temperatures pretty cold. 17, is that what it said? Or you didn't say it all? No, it was 17 in the morning. It was 12 degrees here as well. In upstate New York, near Lake George, for any of you folks that know the upstate area. Wood Spirit is in Bristol. I know exactly where that's at. So definitely feeling the weather temperatures up here in the Northeast and along the east, the Midwest, Ohio Valley, Northern Plains, obviously. And we have fire season to talk about. It happens every year. It's a cycle. There's nothing we could do to stop this. Even if everybody stopped using lighters or matches or fireworks, there's still lightning out there. There's still dry weather conditions that create these problems in the first place. All we can hope for is that the firefighters out there can contain this fire and keep it to a minimal. Right now, it's burning nearly through about 4,000 acres, which we have seen much higher acreage being burnt from these fires. But we're dealing with the Santa Ana winds, and thus far, that is why we have these three fires: the Palisade Fire, the Eaton Fire, and the Hearst Fire. 100 acres there for the Hearst Fire. The Eaton Fire, it looks like we have 1,000 acres being burnt right now. And then we have the Palisades Fire, which is burning roughly 3,000 acres. So let's hope that they can contain this situation and keep it under control here and keep it light like it is right now. But it looks pretty scary, too, if you guys had watched some of the footage online. Powerful earthquake. This is a couple days old. 7.1, leaving over 120 dead. This is in Zhang, China. Now, when this news broke, the death toll was just over 15. To see now that we're over 120 fatalities, that's pretty rough. Again, we believe there's a connection between solar activity and seismic activity here at the Grand Solar Minimum channel, just like Willie Soon, just like John Casey. At least 6 dead from this winter storm, 300,000 people without power. This is the one that just exited the eastern part of the United States. 6 people have been reported dead during the strong winter storm Blair on January 3rd, causing hundreds of crashes. My brother in Ohio actually was involved with an accident by himself, but blew out 2 of his tires, did some front end damage. The roads are no joke. In fact, kids are still missing school from that storm on the 3rd. So, I'm sorry, the 6th and the 7th, and now today's the 8th. So this is the 3rd day that kids in the Ohio Valley, in the Dayton region, missed school for 11 inches, 10 inches, tops. So, a couple road deaths here, and it's not important to me. Unfortunately, their souls, I pray for their families, but let's not glorify the bad stuff here. Unfortunately, it happens, right? I don't mean disrespect. Sometimes I feel like a lot of people throw a lot of fear out there in what they report. All right, let's refresh this because I set this up earlier today, and this thing changes so much, guys. In fact, don't take anything as truth past 4 days. So here is today, January 8th. Lots of cold air across the United States. The next system that's coming in from Texas, my goodness. So parts of Arkansas and Missouri, western Tennessee, northern Alabama, northern Mississippi, you're going to get some snowfall, some heavy snowfall. And this storm will, again, travel to the East Coast. Icing possible for the Carolinas. This is for Saturday, January 11th. More light snow across the Ohio Valley, Virginia, Kentucky, Tennessee as well. And again, this snow kind of just breaks apart. It's a light system that goes up to the northeast, and we dodge a bullet. That could have been ripe for a nor'easter. High pressure sets in after that. One little system coming in from the Great Lakes on January 13th. Again, light snow, lake effect more than anything. So not in the entire state of New York will see snow, mainly closer to the lakes. So we're pretty quiet across the United States. Really cold, but quiet across the middle part of January. More lake effect snows affecting the northeast region. And then there's something in the Gulf that's trying to get its act together. And it's when that low that starts up over New Mexico gets together with the low in the Gulf. Here we are, more cold air spilling into the United States. Snow and rain moving across the Ohio Valley. This is January 19th. This will start off as rain in the northeast. Believe it or not, temperatures in the upper 30s. And then will be followed in the back end of this with colder air changing everything to snow. In fact, by the time it changes over to snow in my part of New York, in the upstate region, it'll be dark, heavy snow. So this is a system we'll be watching on Monday, January 20th. This thing will tail out of here. Lake effect snows will trail after that through the 22nd, which is my birthday, by the way. And then that's really it. Again, anything past 4 to 6 days on these models, it's not worth really even thinking about. But us here as weather geeks, we can't help ourselves. Cold air will begin to spill in across this United States here in the middle of January. You see the purple stuff coming down, getting a little bit colder. A brief rigid fridge, and this is where the temperatures support the rain in the low pressure system that's going up the East Coast. They're actually thinking low 40s on January 19th, with a sharp drop in temperatures of Arctic air spilling into the United States Monday, January 20th, and continuing to make its way down south. And really, this could be a whole lot worse. We're just going to keep watching this right now. Nothing to be too crazily concerned about. This is typical winter weather patterns here in January. So, again, folks, I don't see anything crazy or unprecedented. Nothing of that nature. But we are noticing things are changing. Snow totals. Again, this summer was nice and warm, right? Look at the south already with that kind of snow total. This is January 14th. Almost a foot across the southern part of the United States. More snow to come in January 20th. This is right around my birthday. Looking like the Appalachian Mountains are going to protect me and my family. 4 inches, maybe 10 inches in our region. But the heavier stuff will be in northern New York, western New York, parts of West Virginia, which I imagine that would be the mountainous regions. So right now, our future cast on the snow doesn't look too hateful. Typical winter, the temperatures are definitely, in my opinion, average for winter. It is below average for some of us here in the Northeast and in the South. I won't discount that. But overall, it's not warm. I'll tell you that. It's not record warmth. It's not record mild. It's not, there's snow. We have frozen precipitation over most of the country right now, except for the western part of the United States. And if anybody wants to know why that we're not seeing snow in the western part of the United States, is that because they're in the positive P&A right now. And as long as they continue to stay in that pattern, it's going to continue to spill cold air. Get my handy dandy arrow back. We're going to continue to see this cold come over here into the south, the east, the northeast, the Ohio, the Great Lakes, the northern plains. This area out here will continue to stay in the positive PNA, which is allowing all this colder air to spill into the United States. So this has been a pretty strong start to winter. Like I said, around December 1st up here in upstate New York, that's when we began to see the more freezing temperatures, accumulating snow starting to pile up. We've had a couple of mild days, but nothing too crazy. So I almost want to come back later today and maybe do an update on the models here for the end of the week, as I know a lot of people are wondering if we're going to have a big storm or not. But, you know, as far as the state of affairs for the grand solar minimum, for all of the haters out there who leave comments in our comment sections saying that, oh, Adapt 2030 doesn't even talk about it anymore. Nobody does. So I guess, if anything, folks, you have to understand something. These guys, some of these guys are content creators. And if they want to switch gears and talk about something else, maybe it's more profitable for them, maybe not. It doesn't mean that they don't still have those views of an impending grand solar minimum. It doesn't mean they gave up on the whole idea. But if you haven't noticed, a lot of channels that talk about global cooling and natural climate change get censored very heavily. And if you're monetizing your channel, don't expect to make any money in this topic. So I love how people say because other channels aren't talking about grand solar minimum, it's over. No, they just have other priorities right now. It's still going on. I know I haven't been broadcasting, but I can promise you guys I'm following this every single day. And there's so much content I want to get to. And I think it's worth me trying a little bit harder here to get the chance to talk to you guys and pass along the information again. You know, even if it's once or twice a week, something. But the naysayers, keep naysaying, keep doubting it, because there's still proof out there showing us that everything we talked about, Zarkova's forecast, solar cycle 25's peak is literally almost over. You'll see a sharp decline in solar activity. Everything is coming to fruition with this forecast. Be patient out there. You'll see the changes. You'll see the results. But again, this is not going to happen overnight. All right, guys, that's going to do it for me. Thanks again to WoodSpirit98 for the super chat. Very, very appreciative of that. We set up a goal for 5, but hey, I'll take 1 out of 5 any day. Good to see a lot of people out there. Andrew, nice to see you. Dolores, Burned Remains, Lori A, Lisa B, Knife Collector. Good to see you, my friend. And lots of others in here. Jerome was in here. Wood Spirit, Jesse Vorwald. He is our former farmer friend. I don't think he's doing the dairy farming stuff anymore. I believe he told me. He says he's out. He's out of that business. So stick around, guys. I might do some more surprise broadcasts. I do have a little off time today and the weekend, so lots going on, lots happening, and I got to knock the rust off. So you might hear from me again tonight. That said, hope everyone has a great evening, and we will talk soon. Take care.
Do you like this show? Give us a thumbs up. Want to support us more? Share to your favorite social media platform, buy a t-shirt, or become a Patreon. All links are in the description below.